In May of 2021, a piece of debris smaller than a pencil eraser, moving at over 25,000 kilometers an hour relative to the International Space Station, punched clean through the thermal blanket of Canadarm2, the station's robotic arm, and left a 5mm hole in the metal boom underneath. Nobody saw it happen. Nobody heard it happen. Astronauts on board only discovered the damage days later during a routine inspection, staring at a puncture wound in a piece of hardware that had, moments before impact, been functioning perfectly. That strike happened 400 kilometers above Earth, inside a region so closely monitored that ground controllers track more than 33,000 individual pieces of debris in real time and regularly maneuver the entire station out of the way of anything large enough to be seen coming. Even with all of that protection, something the size of a grain of rice still got through, completely unannounced, at a speed that would have been lethal if it had struck a window, a suit, or a person instead of a robotic arm. Now take that exact scenario and move it somewhere with no tracking network, no ground control, no ability to maneuver out of the way, and no possibility of rescue if something goes wrong. That's not a hypothetical worst case. That's simply what it means to leave the narrow, carefully monitored bubble we currently call spaceflight and head into the actual emptiness beyond it. Humanity talks about deep space travel with a kind of casual optimism that rarely survives contact with the actual engineering and biology involved. We picture starships, colonies, a future where crossing between worlds is as routine as crossing an ocean once became. The reality, based on everything we currently understand about physics, engineering, and human biology, is considerably harsher. And the problems start with something as basic as staying warm, fed, and breathing begin with power, because almost every other system on a spacecraft depends on it, and power in deep space obeys a brutally unforgiving rule of physics called the inverse square law. Move twice as far from a light source, and the intensity of that light doesn't drop by half. It drops by a factor of 4. Move 10 times farther away, and it drops by a factor of 100. This matters enormously for any spacecraft relying on solar panels, which is currently the primary power source for nearly everything humanity has ever sent into space, including the International Space Station. At Earth's distance from the Sun, solar panels work extremely well. By the time you reach Jupiter, roughly 5 times farther from the Sun than Earth, the available sunlight has dropped to only about 4% of what we receive here. Push out to Neptune, 30 times farther from the Sun than Earth, and that number collapses to roughly 0.1%. Past the edge of the solar system, in the kind of true interstellar space a mission to another star would eventually have to cross, sunlight becomes so faint it's functionally useless as a power source at all. The obvious fallback is nuclear power, and it does work up to a point. NASA's Voyager probes, launched in 1977, have survived for nearly 5 decades on radioisotope thermoelectric generators, devices that convert the heat released by the natural radioactive decay of plutonium-238 directly into electricity, requiring no sunlight and no moving parts. But that heat source has a fixed, unavoidable decay rate. Plutonium-238 loses roughly half its radioactive output every 87 years, meaning Voyager's power supply has been quietly, continuously shrinking since the moment it launched. Engineers have already had to permanently shut down individual scientific instruments on both Voyager spacecraft, one by one, specifically to conserve the shrinking amount of power still available, prioritizing which systems get to keep running as others are deliberately switched off forever. Even a perfect nuclear power source, in other words, isn't really permanent. It's a very long, very slow countdown. And for a human crew, rather than an unmanned probe, running out of power doesn't mean losing a scientific instrument. It means losing heat, breathable air, and drinkable water all at once, with nowhere else to draw any of it from. It's worth pausing on just how far a mission would actually have to travel before any of this becomes relevant, because the distances involved make the power and resource problems considerably worse than they might first appear. The nearest star system beyond our own sun, Alpha Centauri, sits roughly 424 light-years away. NASA's Parker Solar Probe, the fastest spacecraft humanity has ever built, reaches speeds of around 692,000 kilometers an hour at its closest approach to the Sun. Even at that extraordinary velocity, sustained continuously in a straight line, the trip to our nearest stellar neighbor would take more than 6,000 years. That number isn't a rounding error or a worst-case estimate. It's the honest, current answer, using the single fastest object humanity has ever launched. Every problem described in this video, the power fall-off, the resource recycling, the debris risk, the radiation exposure, and the physical toll on the human body, would need to be sustained not for a few years, but for a length of time that dwarfs the entire recorded history of human civilization, before a crew traveling at anything close to our current technological limits ever reached even the closest star beyond our own. That leads directly into the second fundamental problem: keeping a crew alive without any possibility of resupply. Every drop of water, every breath of oxygen, and every gram of food a crew consumes on a long mission either has to be carried from Earth or produced and recycled on board. And recycling technology, even at its current best, isn't perfect. The International Space Station's life support system, formerly called the Environmental Control and Life Support System, spent its first decade or so in operation recovering roughly 93 to 94% of the water crew members used, through a combination of humidity capture, urine processing, and filtration. In June of 2023, NASA engineers finally pushed that number up to a genuine milestone: 98% total water recovery, achieved by adding a new component called the brine processor assembly, specifically designed to pull the last remaining usable water out of the concentrated waste byproduct the older system had simply been discarding. That improvement matters enormously, but it's worth being honest about what even 98% actually means over a period of years rather than months. A small, steady leak compounding day after day, month after month, on a mission stretching not just to Mars, but genuinely deep into interstellar space, adds up to a real, unavoidable resource deficit that no amount of careful rationing can fully eliminate. Only delay the obvious instinct, simply carrying more supplies to cover that shortfall, runs straight into a separate, entirely unforgiving piece of physics called the rocket equation. Every additional kilogram of water, food, or spare equipment loaded onto a spacecraft doesn't just need to be launched once. It needs to be accelerated, decelerated, and often accelerated again throughout the entire mission. And doing that requires fuel, which itself has mass, which then requires even more fuel to move that added fuel, in a compounding relationship that grows sharply worse the more total mass you're trying to carry. This is precisely why spacecraft designers treat mass as one of their most tightly rationed resources, weighing every additional bolt and instrument against the fuel cost of carrying it. It's also why simply solving the resupply problem by loading a spacecraft with a decade's worth of extra water and food isn't really a viable option at all. Past a certain point, the fuel required to move that additional mass becomes larger than any realistic spacecraft could carry, which means the resource problem and the propulsion problem aren't actually separate issues. They're the same problem viewed from two different angles, and neither one has a clean, independent fix. The most vivid warning about just how difficult a fully closed life support system actually is came not from a spacecraft at all, but from an experiment conducted entirely on the ground. In September of 1991, 8 people sealed themselves inside Biosphere 2, a 3-acre glass and steel structure built in the Arizona desert, specifically to test whether a completely self-contained, artificially built ecosystem could sustain human life indefinitely, with the explicit long-term goal of learning what a future Mars habitat or deep space vessel might require. The facility contained miniature versions of several of Earth's major biomes: a rainforest, a small ocean with a coral reef, a desert, and an agricultural zone meant to grow the crew's food, all sealed off from the outside world. Within the first 16 months, something nobody had fully anticipated began happening. Oxygen levels inside the sealed structure steadily dropped from a normal 9% down to roughly 14 T to 14. 4%, a concentration comparable to standing on top of a mountain over 4,000 meters high, thin enough that crew members reported persistent fatigue, difficulty concentrating, and disrupted sleep. It took months of investigation to work out exactly where the oxygen was actually going, and the answer turned out to be almost absurdly mundane. Soil microbes inside the facility, feeding on unusually rich organic material in the imported soil, were consuming oxygen and producing carbon dioxide far faster than the enclosed plant life could photosynthesize it back out, while at the same time, the facility's own concrete structure was slowly absorbing carbon dioxide directly out of the air through an ordinary chemical reaction nobody had accounted for in the original design. Engineers eventually had to pump in emergency oxygen from outside just to keep the crew safe, quietly breaking the one rule the entire 2-year experiment had been built around. Biosphere 2 wasn't a failure because closed ecosystems are impossible. It was a genuinely valuable, sobering demonstration that a sealed environment includes every single surface and organism inside it, down to bacteria in the soil and chemistry in the walls, any one of which can throw the entire balance off in ways nobody predicted in advance, on a planet where if something goes wrong, you can at least open a door. Space, meanwhile, isn't the calm, empty backdrop it appears to be in photographs. It's populated by an enormous quantity of fast-moving debris, natural micrometeorites, and closer to Earth, humanity's own accumulated space junk. And the danger isn't really about size, it's about speed. Relative velocities between a spacecraft and debris in orbit can reach tens of thousands of kilometers an hour. And at those speeds, even genuinely tiny objects carry a staggering amount of kinetic energy, since the destructive force of an impact scales with the square of velocity, not simply its mass. A 2021 report from NASA's Office of Inspector General estimated that low Earth orbit alone contains more than 26,000 pieces of debris large enough to destroy a satellite outright on impact. over 500,000 pieces the size of a marble capable of seriously damaging a spacecraft, and more than 100 million fragments as small as a grain of salt, still large enough to puncture a spacesuit. The Canadarm2 strike wasn't an isolated fluke either. Later that same year, in October of 2021, the ISS's Russian Nauka module suffered a separate micrometeorite impact that punched a hole clean through a radiator, venting 72 liters of coolant directly out into space before the leak was brought under control. And this all happened in the one region of space humanity actually tracks and defends against, close enough to Earth that ground stations can watch for incoming threats and command evasive maneuvers when something large enough is spotted on a collision course. Once you leave that monitored zone, none of that protection exists anymore. There's no ground station tracking debris 100 million miles from Earth, no early warning, and no possibility of an evasive maneuver against something you never saw coming. A single unlucky impact on a hull, a power system, or a water recycling unit, with no rescue possible and no spare parts beyond whatever the crew happened to bring, could end a mission instantly. And there would be no way to predict, prevent, or even fully explain it afterward. Even a spacecraft that avoids every piece of debris and never loses a drop of water still has to contend with the single most stubborn problem of all, the fact that the human body itself simply wasn't built for this environment, and nowhere is that clearer than in what happens from radiation exposure. On Earth's surface, you absorb roughly 3 millisieverts of background radiation over an entire year, shielded by both the planet's magnetic field and its atmosphere. Astronauts aboard the International Space Station, still largely protected by Earth's magnetic field even at orbital altitude, absorb roughly 150 millisieverts a year, around 50 times the surface rate. Beyond that magnetic shield, in true deep space, the exposure climbs dramatically further, driven by galactic cosmic rays, extremely high energy particles from outside our solar system that conventional shielding struggles to stop, and which can, under certain shielding configurations, actually produce a secondary shower of dangerous radiation when they collide with spacecraft material. NASA currently limits its astronauts to a career radiation dose corresponding to roughly a 3% increase in lifetime fatal cancer risk, a threshold that real mission calculations for something as comparatively short as a round-trip Mars mission already come uncomfortably close to or potentially exceed. A mission stretching across years of true deep space transit with no planetary atmosphere to duck into at any point along the way would push crew members' cumulative exposure into territory current medicine considers to carry a functionally guaranteed, significantly elevated cancer risk. And unlike a sunburn or a broken bone, radiation damage to DNA doesn't fully heal. It accumulates quietly across every day of the mission with no way to reset the clock once the crew is back on solid ground, if they ever get there at all. Radiation isn't the only way the human body starts breaking down in space either. Remove Earth's gravity for an extended period, and the body responds by treating your own skeleton as expendable weight. Astronauts consistently lose bone mineral density at a rate of roughly 1 to 2% per month, while weightless, concentrated most heavily in exactly the weight-bearing bones you'd need most upon returning to any planetary surface, the hips, spine, and legs. Extrapolate that rate honestly across a period of years rather than months, and the math becomes genuinely alarming. a real possibility of losing somewhere in the range of a third to more than half of total bone density over a multi-year mission, even accounting for the roughly 2 hours of daily resistance exercise astronauts currently use to slow, though never fully stop, the decline. Muscle mass follows a strikingly similar trajectory, atrophying without the constant resistance of gravity to maintain it, particularly in the legs, back, and core, the exact muscle groups needed simply to stand upright again afterward. The heart, itself a muscle, undergoes its own quiet transformation, gradually losing mass and shifting shape as it adapts to no longer needing to pump blood upward against gravity's pull, an adaptation that becomes a serious liability the moment that same heart has to suddenly perform against gravity again, whether on a distant planet's surface or back on Earth. Astronauts returning from even standard 6-month ISS missions frequently experience dizziness, a racing heart, and occasional fainting spells simply from standing up too quickly in the days after landing, a condition called orthostatic intolerance. And there's no reason to believe a body reshaped by years, rather than months, of weightlessness would handle that transition any better. The changes don't stop at bones, muscles, and the heart. Fluid inside the body, no longer pulled downward by gravity, shifts upward toward the head and chest, producing a puffy, swollen appearance in the face that astronauts have informally nicknamed puffy face syndrome, alongside a persistent feeling of nasal congestion that never fully resolves for the length of the mission. That same upward fluid shift raises pressure inside the skull, and NASA has documented real, sometimes lasting structural changes to the eye as a result, a condition now formally called spaceflight-associated neuroocular syndrome, involving swelling of the optic nerve, and in some astronauts, literal flattening of the back of the eyeball, producing vision changes that in a meaningful number of cases have persisted for years after return to Earth, and in a smaller number of documented cases appear to be permanent. The immune system weakens too, measurably, with several studies documenting the reactivation of ordinarily dormant viruses, including strains related to chickenpox and herpes, in astronauts during extended spaceflight. A genuinely concerning finding for any future crew facing a medical emergency with no hospital within months of travel in any direction. Even something as small as a minor wound heals more slowly in orbit than the same injury would on Earth, a detail that sounds minor in isolation but becomes considerably more serious stacked alongside everything else already working against a crew's health during a years-long mission. And underneath every physical symptom sits a psychological burden that's arguably just as serious and considerably harder to measure or treat from a distance. Confined for years inside a small sealed environment with no ability to step outside, feel actual wind or sunlight, or meaningfully vary the daily routine, astronauts on even relatively short ISS missions have reported documented struggles with sleep disruption. Since there's no natural day-night cycle to anchor the body's internal clock, along with measurable periods of anxiety, low mood, and cognitive fog. Ground-based isolation research, including studies conducted at NASA's Hera facility at Johnson Space Center, a sealed 3-story habitat specifically built to simulate the confinement, restricted communication, and mission stress of a long-duration deep space flight, has consistently found that even carefully screened, extensively trained volunteers show real signs of psychological strain the longer an isolation period stretches on. Crews participating in these analog missions, sealed inside Hera for periods of up to 45 days at a stretch, have shown documented changes in mood, sleep quality, and team cohesion, and researchers running similar isolation studies at Antarctic research stations have identified a recurring pattern they call the third quarter phenomenon, a measurable dip in morale that tends to appear once a mission is well past its midpoint, but still has a considerable stretch left to go. And crucially, every one of these ground-based studies still includes a genuine emergency exit, a door that can be opened if something goes seriously wrong. A true deep space mission offers no equivalent option. There is no early return, no emergency evacuation, and no way to simply step outside for even a few minutes of relief from the same four walls, the same faces, and the same manufactured lighting for as long as the mission requires. None of this means humanity is permanently barred from deep space, and it's worth being precise about what these findings actually establish versus what they don't. Every single limitation described here is a problem rooted in today's specific technology and today's specific medical countermeasures, not a permanent, unchangeable law of the universe the way the speed of light is. Better shielding materials, more efficient closed-loop life support systems, building directly on the lessons learned from both the ISS and Biosphere 2, artificial gravity generated through rotation, and pharmaceutical countermeasures for bone and muscle loss are all active, funded areas of ongoing research, not abandoned dead ends. Engineers have studied rotating spacecraft designs capable of simulating Earth-like gravity since at least the 960 seconds, and the physics behind the concept isn't seriously disputed. What's missing isn't the theory. It's a crude vehicle actually built and flight tested at the scale required to make the idea work comfortably over a period of years, something no space agency has yet attempted. Radiation researchers, meanwhile, continue testing new shielding materials, including hydrogen-rich polymers, and even water itself, arranged strategically around a crew's living quarters, though none of these approaches yet fully solves the problem posed by the highest energy galactic cosmic rays, the specific component of deep space radiation that conventional shielding struggles with the most. But it would be dishonest to pretend those solutions already exist in a form ready for a genuine multi-year deep space mission today. They don't. What the current evidence actually shows, consistently across radiation science, closed ecosystem engineering, orbital debris statistics, and decades of human spaceflight medicine, is that surviving deep space for years or decades isn't simply a matter of building a bigger rocket with more fuel. It's a problem stacked on top of other problems: power, water, radiation, collision risk, bone density, cardiovascular health, vision, immune function, and psychological endurance, all failing simultaneously along different overlapping timelines, each one capable of ending a mission entirely on its own, with absolutely no backup plan once you're far enough from home. That rescue simply isn't a word that applies anymore. We built a space station 400 kilometers above Earth's surface, practically within shouting distance by cosmic standards. And even there, keeping a handful of astronauts alive requires constant, round-the-clock support from thousands of people on the ground, continuous resupply missions, and a genuine, real, if rare, history of near misses from debris nobody saw coming until after it had already struck. That's the safest, most heavily supported environment humanity has ever managed to sustain human life in beyond Earth's own surface. Deep space, the true unsupported emptiness beyond it, removes every single one of those safety nets at once and asks a human body evolved over hundreds of thousands of years for one very specific planet to simply endure the absence of everything that body was built around for years with no way back if something breaks. If stories like this pull you in, subscribe to the channel, because this is exactly the kind of territory we spend our time exploring here. Drop a comment and tell me which part struck you hardest. The fact that a piece of debris the size of a grain of rice already punched through hardware on the ISS, the 8 scientists in Arizona who nearly ran out of breathable air in a sealed glass building, or just how quickly a healthy human skeleton starts breaking down the moment gravity disappears. Let me know where in the world you're watching this from, and if you want to keep exploring, there's another documentary waiting for you right here on the channel. So stay a little longer, and let's keep looking up.